Welcome back. In this lecture, we are going to discuss on uncertainty principle. According to uncertainty principle, it is fundamentally impossible to determine two conjugate pair of variables simultaneously to an accuracy greater than h cut by 2, where the reduced Planck constant h cut equals to h by 2 pi, h being the Planck's constant. So in other words, if one of the variable of the conjugate pair can be measured with high accuracy, then simultaneously the other variable cannot be measured with high accuracy. For to understand it, let us consider some conjugate pair of variables like position and momentum along that direction. That means, say a particle is restricted to move along x direction only. So it is x direction and the particle is moving along that direction only. Then if we try to measure the position of that particle at any instant, say x is the position of the particle at any instant x, at any instant t, and the momentum along the direction x is px. And if we want to measure x and px simultaneously, then it is impossible to determine both the quantities with high accuracy. So if there is some uncertainty in measurement of position x as delta x and the uncertainty in measurement of momentum along x direction as delta px, then both of these two uncertainties cannot be close to zero. That means if position is measured with high accuracy, delta x would be very close to zero. In that case, the uncertainty in measurement of momentum, that is delta px, would be very high. On the other hand, if it is possible to measure momentum with high accuracy, then there will be a large amount of uncertainty, that is delta x, in measurement of position x. So delta x in that case will be very large. So you cannot measure momentum and position simultaneously with high accuracy. But the point is, here both the quantities must be measured along a particular direction. So if we assume the particle is moving along y direction only, then the conjugate pairs would be y and py, that is position along y direction and momentum along y direction. These two quantities act as the conjugate pair of variables. We cannot measure y and py simultaneously with high accuracy. If there exists a very small uncertainty in measurement of one quantity, then the uncertainty in measurement of the other quantity will be very large. And again, this restriction imposed by uncertainty principle only valid for position and momentum along the same direction. That means if we consider position along x direction and momentum along y direction, they can be measured simultaneously with high accuracy. Or position along x direction and momentum along z direction, that can also be measured. Or y px, y pz can be measured simultaneously with high accuracy. Similarly, z px and z py can also be measured. But x px, y py or z pz cannot be measured simultaneously with high accuracy. Other type of conjugate pairs are like energy and time. That means it is impossible to determine energy and time simultaneously with high accuracy. Both both of these two quantities cannot be measured with high accuracy simultaneously. Other type, say angular momentum and angular position. Mathematically, if we consider the position and momentum conjugate pairs, then if delta x and delta px be the uncertainty in measurement of position x and momentum px along x direction, then the product of delta x and delta px is always greater than equal to a constant. That constant is assumed to be h cut by 2. Therefore, we observe that the product of uncertainty is greater than equal to a constant value, say h cut by 2. So if one quantity is measured with high accuracy, if one quantity say x is measured with high accuracy, that means the uncertainty in measurement of x, that is delta x, will be very small. Then according to this form, delta px would be very large. If delta x is very small, then delta px should be very large so that right hand side remains constant. If one quantity is increased, other quantity should be decreased, or vice versa. So if delta px is very small, that means momentum along x direction is measured with high accuracy, so that uncertainty in measurement of momentum is very small, then uncertainty in measurement of x will be very large, so that right hand side remains constant. Similarly, if we consider delta E and delta T with the uncertainty in measurement of energy and time, then according to uncertainty principle, the product of delta E, that is uncertainty in measurement of energy and uncertainty in measurement of time, should be greater than equal to h cut by 2. So if we consider an energy level whose energy is E and the time of stay of an electron in that energy level be T, then we cannot measure both the energy of that state and time of stay of the electron in that energy state simultaneously with high accuracy. So if delta E is measured, or better to say, if energy E is measured with high accuracy, delta E will be very small. In that case, delta T, that is measurement uncertainty in time, will be very large. We can apply uncertainty in different cases, like we can prove that an electron doesn't exist within a nucleus. And for that, first thing, we assume that an electron does exist within the nucleus. Because our assumption is that the electron exists within a nucleus. And if we assume that radius of that nucleus is r and the electron is restricted along x direction only, then electron can be anywhere within this diameter of the nucleus. Therefore, the uncertainty in position of that electron is equal to the diameter of the nucleus. Since most of the element has nucleus of diameter of the order of 10 to the power minus 15 meter, so uncertainty in position of an electron, if the electron exists within the nucleus, will be 2 into 10 to the power minus 15 meter. So that is the uncertainty in position of that electron within the nucleus. Then according to uncertainty principle, we can say the uncertainty in momentum of that electron would be greater than equal to h cut by twice delta x, because we know the product of the two uncertainties is greater than equal to h cut by 2. Therefore, delta px would be greater than equal to h cut by twice delta x. H cut by twice delta x is the minimum value of the uncertainty in measurement of momentum. That means momentum uncertainty starts from this value, h cut by twice delta x, and it can be any high value, but the minimum uncertainty in measurement of momentum would be h cut by twice delta x. Therefore, we can write the minimum uncertainty in momentum, that is delta px min, would be h cut by twice delta x. If we put the values of h cut as h by 2 pi and uncertainty in position delta x as 2 into 10 to the minus 15 meter, then we get the value, minimum uncertainty in momentum value as 2.636 into 10 to the minus 20 kg meter per second. So this is the minimum uncertainty in momentum of that electron, which we assume to exist within the nucleus. Then what would be the minimum value of momentum? So since the electron is moving within the nucleus, it has some momentum. So what would be the minimum momentum value of that electron? To find it, let's have this logic that say we want to measure a length L. We want to determine the length of this line, and the measurement error comes out to be say delta L. Maybe it is due to inaccuracy of the instrument we are using. So delta L is the measurement error or inaccuracy of the instrument used. So if we know the measurement error as delta L, then one thing we can say that the measured value, that is the measured value length, cannot be less than this delta L. The measured value of the length cannot be less than the error itself. So minimum possible value of the length, minimum possible value of the length would be the error delta L. So if we use the same logic here, we know the minimum uncertainty in momentum as 2.66 10 to the minus 20 kg meter per second. Therefore, the minimum value of momentum would be this, because it cannot be less than the uncertainty in momentum. So we can say that if the electron exists within the nucleus, the minimum momentum value can be 2.66 into 10 to the minus 20 kg meter per second. And if we know the momentum of the electron, then from the relativistic mechanics, we can estimate the total energy of that electron. Since the momentum we have is the minimum momentum possessed by that electron, the energy of the electron would be the minimum energy. So the minimum energy E min would be P min square C square plus m naught square root of 4 whole square root, where C is the velocity of light in free space, that is 10 to 10 to the power 8 meter per second. M naught is the rest mass of the electron, which we know as 9.11 into 10 to the power minus 31 kg. So if we put those values, then energy value comes out to be 7.908 into 10 to the minus 12 joule. By the way, here the second term is very small with respect to the first one. So during calculation, this second term can be neglected also. Now, since the joule energy in joule comes out to be very small, we can write it in terms of electron volt as 49.4 mega electron volt. That is 49.4 into 10 to the power 6 electron volt. Therefore, if we assume that the electron exists within the nucleus, then the minimum possible value of momentum of that minimum possible value of energy of the electron would be 49.4 MeV. So if the electron exists within the nucleus, its minimum energy should be greater than 40 MeV. Whereas it is experimentally observed that the maximum energy for beta decay, even for radioactive nuclei, is of the order of 4 MeV. Even for radioactive nuclei, the maximum energy for beta decay comes out to be 4 MeV, of the order of 4 MeV. Whereas what we observed, that if the electron exists within the nucleus, then its minimum energy would be greater than 40 MeV, which is impossible. Therefore, the assumption we made that electron exists within the nucleus is not true. So in other words, an electron cannot exist within a nucleus. By that way, we can prove that an electron cannot exist within the nucleus from uncertainty relation. Now, let's do some numericals. The first one, it says compute the smallest possible uncertainty in position of an electron moving with a velocity 3 to 10 to the power 7 meter per second. So velocity of the particle, velocity of the electron is supplied. So according to uncertainty principle, we can write that if we assume the electron is moving along x direction only, then its momentum should be px, momentum along x direction. Then the product of the uncertainty in measurement of x and px could be greater than equal to h cat by 2. So uncertainty it can be set. Now since momentum along x direction is the product of mass of the electron and its velocity along the same direction x, therefore delta px is m delta vx. Now according to question, this Vx is supplied as 3 into 10 to the power 7 meter per second. And delta x needs to be estimated. So this one needs to be estimated. So we don't know this value. And instead of delta Vx, Vx is supplied. According to the question, velocity along x direction is supplied. Whereas we require the uncertainty in measurement of velocity, that is delta Vx is required. So if we use the same logic as used before, mean the maximum uncertainty in measurement of velocity is the velocity itself, because our uncertainty in measurement of a quantity cannot be greater than the quantity itself. Measurement error cannot be greater than the measured value. Therefore, maximum possible value of uncertainty in measurement of velocity is velocity itself. Therefore, we can say delta Vx max can be 3 into 10 to the power 7 meter per second. Therefore, the minimum uncertainty in measurement of position, can be estimated as h cat by twice m delta Vx max. Now, all the quantities here are known, so we can put the values. Delta x mean comes out to be 1.93 10 to the power minus 12 meter. So that is the smallest possible uncertainty in measurement of position of that electron. Similarly, the problem 2, it says that find out the minimum uncertainty in energy state of an atom if the electron remains in that state for 10 to the power minus 8 seconds. So consider an energy state of energy value E and time of stay of an electron in that energy state is T. Then according to the question, T is 10 to the power minus 8 seconds. T is 10 to the minus 8 seconds. Now we have to estimate the minimum uncertainty in measurement of energy. That means we need to estimate delta E mean, the minimum possible value of measurement uncertainty in energy. So again, if we use uncertainty principle, delta E into delta T greater than equal to h cat by 2, where delta E is the uncertainty in measurement of energy and delta T is the uncertainty in measurement of time of stay of the electron in that energy level. And since T is given, maximum value of uncertainty in measurement of time can be time itself. Therefore, delta T max is 10 to the power minus 8 seconds. Delta T max is 10 to the power minus 8 seconds. Therefore, the minimum uncertainty in energy state of the atom, would be delta E min, which will be h cat by twice delta T max. So delta T max is known. If we put the value of h cat, we can estimate the minimum uncertainty in measurement of that energy comes out to be 3.29 into 10 to the minus 8 electron volt, that is 32.9 micro electron volt.